Well, hello, and welcome to the Spring 2022 section of Math 407 at Cal State Fullerton. This is a senior level class in abstract algebra, so it has a few prerequisites that I assume everybody is familiar with. In particular, I assume everybody's familiar with the material in Chapter 0 of the textbook relating to sets and relations and functions and that sort of thing. However, I know that it could have been a while, so the idea of this video is to give us a little bit of review on relations and functions and equivalence relations so we can get a really strong start to the semester. That's exactly what we're going to talk about here. So we're going to talk about relations, functions, and equivalence. I'm going to assume for all of this that we're all pretty familiar with dealing with sets and writing down sets and the notation for that based on all the math courses that we've had leading up to this course. Now, if that is not the case, then I strongly suggest that you review very carefully the material in Section 0, and even if you are, reading through Section 0 and doing the exercises is going to be pretty helpful. But let's go ahead and start out with a very basic definition, a very important definition too. So for this, let A and B be sets. A relation from A to B is just a subset R of the Cartesian product A cross B. It's actually a pretty straightforward definition. I know what a subset is, hopefully. I know what the Cartesian product is. So relations are very basic objects. Now, oftentimes the way we use them looks a little bit different and kind of hides the fact that they're really just subsets of the Cartesian product. Specifically, we write ARB to mean that the ordered pair AB is an element of that set R. Remember, elements of the Cartesian product are going to be these kinds of pairs. So if I have a subset, it's a subcollection of those pairs. So writing ARB is really just saying that that particular pair belongs to this particular subset. And that might seem a little bit strange, but this actually comes from the way that we use and define relations typically. It also sort of rolls off the tongue because ARB is kind of like saying A is related to B. So let's do a particular example. I'll let A be the set of all residents of Orange County, and I'll let B be the set of all residents of LA County. And I'll define a relation by saying that a relation from A to B by saying that X are Y if and only if X and Y are siblings. So in this case, my relation says that X is related to Y if X is in Orange County, Y is in LA County, and X is the brother or sister of Y. This is kind of a fun example because here relation really, kind of means, well, a relation, like a relative. Now, oftentimes, we're going to be really interested in the specific case when A and B are the same set. That leads to the following definition. A relation on a set A just means a relation from A to A. That is to say, it's a subset of the Cartesian product A cross A. So let's also do an example of something like this. Maybe this time a little bit closer to some math. So I'll let A be the set 1, 2, 3, 4 and define a relation R on A by saying MRN, that is M is related to N via this relation R, if and only if M times N is even. So this defines an example of a relation on the set A, a relation from A to A. And because relations are subsets of the Cartesian product, we can also write it down a very different way just by expressing it as that corresponding subset. So we start out by describing the Cartesian product. This is all pairs Mn such that M and N are in A. And we can write this all out explicitly. A has 4 elements, so A cross A is going to have 4 times 4, which is 16 elements, which we can write out like this. So the relation that we defined is going to be a particular subset of that set we just listed, consisting of all pairs M and N. So M and N are in A, and M times N is even. And we can just go through our list here and figure out which ones of these satisfy this property. The product is even. So not this guy, certainly this one, all these guys that I'm underlining have products which are even, and the ones that I've skipped underlining do not satisfy that property. So this allows us to write down explicitly what our relation is as a subset of the Cartesian product. So we've seen a couple different ways to express a relation. Now relations fall into two really important subtypes. That is not to say that all relations are of one of these two types, but these are just the two most important. The first are functions, and the second are equivalence relations. And just take a minute to appreciate this. All the things, the main objects of study for a long time in our mathematical experiences, from pre-algebra up through advanced calculus and differential equations and linear algebra, are functions. And functions are just special relations. So relations here are really fundamental building blocks of a lot of mathematics that we have already been appreciating for a long time. In this class, in this semester, we're going to get really into the second one, the equivalence relations, because these are going to be fundamental building blocks of a lot of constructions in abstract algebra, like quotient groups, quotient rings, all kinds of things like this. And maybe you've seen some examples of what I'm talking about here with these quotients before, back in linear algebra, and maybe you haven't, and that's okay too. But let's talk about these two different kinds of relations here. Reminding ourselves again that these are not the only two kinds of relations, but these are by far the two most useful and most important kinds of relations. Functions and equivalence relations. And it's really key here to remember that functions and equivalence relations are very different. Functions and equivalence relations are basically entirely different kinds of relations, and there's no overlap, except in very trivial cases. It's really difficult to be both a function and an equivalence relation at the same time. The only way that can happen is if the sets that we're working with, A and B, are the same sets and they're singletons, or more generally, A and B are the same set. Oh, I gotta even take that back. That's the only case. A and B have to be the same set, they both have to be singletons, and our relation is just that non-trivial subset of the Cartesian product. Not a very interesting case. So this big line I'm putting here is put here for a pretty good reason. Now let's start out by defining functions. A function is a relation R from A to B satisfying a very particular property. For every A in A, there is a B in B with ARB, that is to say with A related to B via the relation R. And moreover, the value B corresponding to that A is unique. So what is this saying? It's saying that for every element in that A, it's going to be related to an element in B and B, and it's going to be a unique element. So the relation is taking A and associating it with a unique B. This is exactly what a function does. It takes an element A to an element of B. And because this is an important new thing, we establish even another notation for this. We write R of A equals B to mean ARB. And R of A equals B is closer to that function notation that we're much more used to from our calculus experience and our previous algebra experience and so on and so forth. Also, instead of using a fancy R like we're doing, we might use a lowercase f or a lowercase g or whatever you might happen to prefer to denote your function. On the other side of things, equivalence relations are not relations from A to B, but they're always relations on a set A. That is to say, relations from A to A. So specifically, an equivalence relation on A is a relation R on A satisfying three properties. First of all, it's reflexive. That means that ARA, for all A in A, every element of A is related to itself. It's symmetric, which means that A is related to B if and only if B is related to A. And finally, it's transitive, which means that if A is related to B and B is then related to C, well then we could say that A itself, starting out there, was related to C. So an equivalence relation has to have all three of these properties. It needs to be reflexive and symmetric and transitive. In this class, we're going to deal with a lot of examples of equivalence relations, but let me give you maybe one or two starting out right now. Let's let A be the set of integers, which I'll denote by Z in the usual way. And I'll say that A R B if and only if A minus B is even. And let's check together here that this is an equivalence relation on Z, those integers. So in order to check this, I want to check all three of those properties. First of all, I want to check that it's reflexive. That is to say that each element is related to itself. So let's go ahead and choose an element. Then I know that A minus A is equal to 0, and 0 is even. So as a consequence, A is related to A by definition. So we've got reflexivity. I also want to check that it's symmetric. That is to say that if A is related to B, then B has to be related to A. So why don't we go ahead and start out by choosing A and B and Z with A related to B. What does that mean? Well, that means that A minus B is even, and a negative of an even number is also even. So I get that negative A minus B is even. And negative A minus B is the same thing as B minus A. But since B minus A is even, I can conclude that B are A. So starting out with ARB, I get BRA. And that proves that the relation is symmetric. And finally, I want to show this relation is transitive. That is to say, I want to show that if A is related to B and B is related to C, well then A is related to C. So let me start out by taking A, B, and C to be integers with A related to B and B related to C. I think you see where I'm going with this, right? I'm immediately going to unwind that definition of the relation itself. It says that A minus B is even, and also B minus C is even. And I'm trying to show that A is related to C. That is to say that A minus C is even. And the way I can do that is I can just take these two even numbers and add them together. And remember, when I add an even number to another even number, hey, it remains even. So we get that A minus C, which is the same thing as A minus B plus B minus C, is the sum of two even numbers and is therefore even. And this means, by definition, that A is related to C. So what we've shown is that if A is related to B and B is related to C, then A is related to C. And that's that transitive property. So we have reflexive, symmetric, and transitive, and therefore we're in equivalence relation. One of the things you might not have talked about in your past courses is why equivalence relations are so useful and so important. And one of the things that, the thing really it comes down to is that equivalence relations define what are called partitions of that particular set. Conversely, in fact, a partition of a particular set defines an equivalence relation. And what is a partition? Let's think about our set as some sort of big amorphous object. What a partition does is it sections off the set A. Why don't I go ahead and label this set as that set A that we've been working with the whole time? Our partition cuts it up into a bunch of disjoint pieces. So it's like dividing it up. A pretty natural kind of thing to want to do in a lot of different places. I mean, this is something we might want to do at home when we're cooking or something like that. So of course, mathematically, it's going to be very useful to have some sort of equivalent kinds of way of chopping things up into certain subparts that might be interesting to look at individually or look at the relationships together, something like that. And this is exactly what a partition is. It takes a set A and divides it into a bunch of subsets, say A1, A2, A3, A4, A5, and so on. And as we can see from the picture here in the partition, all these different subsets are disjoint. They have no overlaps. And their union is the whole thing. I haven't thrown any parts of my set away. So the definition of a partition is just going to capture those two properties. A partition of A is a collection of subsets A1 through AN of A, satisfying two properties. They're pairwise disjoints. The intersection of AJ with AK is the empty set for J not equal to K, and their union is A. A1 union A2 union all the way through AN, they all add up to A. So that's what a partition is. Now, equivalence relations give rise to the partitions via objects called equivalence classes. So to define this, let's let R be an equivalence relation on A, and let's let little a be an element of A. Then we can define the equivalence class of that element little a, and it's denoted using square braces, or sometimes denoted using just a with an overbar, just depending on the notation of what you're reading. And it's a set. It's a specific subset of A consisting of all elements of A which are related to A. So the equivalence class of A is the set of all X in big A such that little a is related to X. And one of the important theorem here is the following. The set of equivalence classes of A forms a partition of A. Let's look at this in the context of the previous example of an equivalence relation. So there, I was thinking about an equivalence relation on the set of integers, and A was related to B if and only if A minus B is even. So let's try to work out some equivalence classes here. I can think about, for example, the equivalence class of 0, so that's 0 bar, and this is going to be the set of all X such that 0 are X. Let's unpack this a little bit. This is the set of all X such that 0 minus X is even. Well, the only way for 0 minus X to be even is if X is even, right? So this is the set of all X such that X is even. And if I want to write that out in some sort of element-wise form, you know, it's going infinitely in the negative direction and the positive direction. So I've got like dot 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 minus 6 minus 4 minus 2 0 2 4 6 and dot dot dot, so on and so forth. So this is the equivalence class of 0. We can also find the equivalence class of, say, 1. And this is going to be the set of all X such that 1 are X. And we can unpack that again. This is the set of all X such that 1 minus X is even. Now, the only way for 1 minus X to be even is if what? If X is odd. So the equivalence class of 1 is the set of all odd integers. And again, we can write this out explicitly if we want to. And it's going infinitely in the negative direction and the positive direction. And we can keep going here. I can think about the equivalence class of 2. Let's try this again. So this is going to be the set of all X such that 2 are X. So this is the set of all x such that 2 minus x is even. Wait a minute. This is the only way for 2 minus x to be even. 2 is even, so minus x would have to be even, so x would have to be even. So this is the set of all x such that x is even. But wait a minute, we already did that one. That is actually the same as the equivalence class of 0. So the equivalence class of 2 and the equivalence class of 0 are the same. Likewise, I can check out the equivalence class of 3, and with a little bit of work, I can show that's the same thing as the equivalence class of 1. And we end up with a sort of pattern here. I think you guys see all the odd numbers, the equivalence class of each odd number is going to be the same as the equivalence class of 1, and each even number is going to have the same equivalence class as the equivalence class of 0. So if I write down all of the equivalence classes without any repeats, I just have 2, 0, and 1. And I claim that these form a partition of the set of integers, and of course they do. What they're doing is they're partitioning the integers into the even integers and the odd integers. And their intersection is trivial, of course, because an integer can be both even or odd. So I can see that. Their intersection is empty. And their union, well, each integer has to be either even or odd, so their union is the whole thing. So we got a partition, just like we thought we would. Not too bad. Okay, so that was a lot to take in so far. Hopefully a lot of this was review. If it wasn't, don't panic. There's a lot of great material that you can review in section 0 of the textbook, and a lot of great exercises at the end of section 0. If you have any further questions, don't hesitate to reach out. You're welcome to email me or also post under the video. That's all for now. I'll see you guys next time.